Hello, my name is Stuart Wortley and welcome to our presentation looking at simulation and fabrication. In particular, we're looking at BS 5395, which is the code and practice for stairs, ladders and walkways within the UK. I put this presentation together after visiting a customer of ours, T&I Solutions, over here in the southeast of England. These guys are specialists with complying with the working at height regulations, and such so that they create things like fixed handrails, gantries, rolling ladders, staircases, and in the example that we do is using here, a step over. Now I'd like to thank the guys down at T&I, Ian, Adam and Ben, who kind of came through with this design. They have been using SolidWorks for a fair few years now, and as such have actually automated a lot of their design process, so it's actually fairly easy for them to quote for any new jobs involving a lot of their standard components. However, recently they've been asked to prove that they do comply to BS 3595. So this is either going to involve them sending it out to another test house, which is going to cost them money and time, or they're looking to see how could they bring this in-house and do it themselves. They knew SolidWorks might be able to help, but they had no idea of how to apply the testing inside the software. So we became involved and we showed them how we could actually prove that their designs comply with the standards. So just what tests do we need to apply to comply with the BS 5395 Part 3 standards? Basically there's two that apply just to the platform. The first is a distributed load of 2000 newtons per metre squared over the gangway, and then we have a concentrated load of 1500 newtons in an area that's only 200 millimetres squared, and we have to choose the kind of what we think is the weakest area of our design. Apart from the obvious mechanical failure, we also need to make sure that the floor does not deflect more than 200th of the span, and also if there's any loaded and unloaded neighbouring sections do not exceed 4 millimeters. More importantly, the standards dictate that we need to verify our designs either by calculations or physical tests, or in other words, we can use SolidWorks simulation to check our designs rather than having to build physical prototypes and testing every time. So what's the plan? Well, first off, we need to simplify the model. We never just chuck our normal SolidWorks model straight into simulation. There's lots of components in there that we don't need, and we just want to try and cut it down so we're just asking the question of the software that we need answering. So it's basically the mechanical parts that really create our design, and we're going to look at some of the options that I choose to simplify it in the next step. Then we need to see if we've got all our materials assigned. Thankfully, if you've been using the SolidWorks materials, then it has all the physical properties to go straight into our simulation tool. If we're using something that's a little bit more exotic, then we might need to go and do a bit of research and find the information off the internet. And there's tools and websites out there such as MATLAB that are a great place for reference material. Now we need to build up our constraints. Now this is probably the hardest part, not in terms of actually physically doing it, but understanding how your tests take place. So we're trying to recreate the conditions if we was doing a physical test on our design, but we're doing it within the virtual environment of SolidWorks. Then it's the fairly easy bit, which is where we actually solve the puzzle. Now this does involve something that's called meshing that you may have heard of about with finite element analysis before, but basically SolidWorks does most of this for you. Effectively what it's going to do is it's going to break the model into lots of little pieces, and then it will actually run all those calculations on those designs to see how far components deflect, and then from those deflections we can work out stresses and strains. And finally we need to look at our results, check our design is okay, and maybe create a report for other people to read. So how did I go about simplifying this model? Well, for starters, I don't need the handrails in this design. They're not that heavy, so they're not adding to the overall weight of the structure, and they're not doing anything structurally. They're not making the support structure any stronger. So all it would do is just slow up the actual solution time, because the model will have to mesh it and check to see, but it's not going to give us anything extra into our design. So I suppress the railings. These gantries rest on these brought in items, these kind of these heavy rubber feet. Now we don't design those, we just buy those in, we know how strong they are, so I don't need to test those, they're not doing anything for our design. I do need to take into account how they're supporting the gantry, but I don't need to actually test the feet themselves. Now all this design is held together by lots of nuts and bolts. However, we know that they're not going to fail because they're basically in shear. But if we add those into our design, that's going to take everything a bit slower. So what we can do is we can delete those out and then we'll apply those as boundary conditions in the next step. The main gantry walkway is from Eurograte. Now that's a kind of a nylon grid structure. Again, if we're going to mesh this up, that's a lot of meshing that's going involved, but we have got physical properties off their website that describe how it behaves. So we can simplify our design down, get rid of all the square holes in the part and just use a flat plate. I'm always looking for symmetry within the design. So in this case we could chop it in half or actually even into a quarter. Now this means that our mesh will be a lot smaller, which means the design will actually solve a lot quicker. So with some of these components I had to create a different configuration. So the Eurograte on the top, I created a separate configuration where it suppressed all the square holes. But to chop this in half, I don't need to go around and create configurations of all the individual steps, so I can just use 1/4. Instead I used an assembly feature and just chopped it into 1/4 of our design. So let's go into SolidWorks now and have a look. So here's the files that T&I sent me. So the first thing I'm going to do is add a configuration called simulation. So I can take off and suppress different models and it's not going to affect their original engineering data. Let's get rid of this concrete base. Now I'm going to use suppress, not hide, because I don't want this to be in the simulation. Let's see what else we can get rid of. So already said about the handrails, they are giving us no structural benefits, so let's suppress that. What else? We've got all the rails on the other side as well, so that was a mirrored assembly, so I'm just going to suppress all of that as well. We've got the feet, so again let's pick all 4 of these feet, going to suppress those. We still have all the nuts and bolts. Thankfully Adam's put those all into a folder, so I can just suppress that folder and that will turn all of them off. And now we've got the platform. So the platform, I've already gone into this part and I created another configuration just where I suppressed off the square holes, so that just swaps it into another panel. And I've also created a little split line on there just so I can put that localized load. Right, I need to chop this into a quarter, so I've just got a sketch that just describes 1/4, or just roughly the outline of 1/4. And then we're going to do an assembly feature, extruded cut. I can do this in both directions and I want to flip the side to cut. So give that a tick and that gives us just that 1/4 of the design. So all I'm going to do now, just hide that sketch and then we can go back to the PowerPoint. The majority of the materials for this design is 1060 alloy. That includes the stringers and the top gantry pole. The treads are using 1060 alloy tread plate, but the tread plate does not affect the strength, so we can just assume it's 1060 alloy. The Eurograte, we had to create a bespoke material. That was taking the material properties that was available from their website. Okay, let's go into SolidWorks again and just make sure it's transferred those materials across. We can only see that if we create a study. So let's go into our simulation tools and we're going to do a new static study. Once we've created a new study, it gives us a few more different options to choose. And the first thing we're going to do here is roll down our different parts. So if we go into each of these parts, we can see the different multi-body design, and then if we hover our mouse over, we can see there's a little tick next to any of these and we can see the material has come across. So in terms of all our metal components, it's showing 1060 alloy steel. So that's great, that's brought it all in perfect. Okay, let's try and find our Eurograte. So we need to open up the little component. We're breaking our way through the different components that are in this little sub-assembly. And we can see here we've got the solid body on the top there, but it hasn't got a material assigned to it. So for right hand mouse button we can apply material. And like I said, this is a bespoke material, so I'm just going to browse down into my custom libraries and I can see the one I created earlier. So it's just giving it all the physical characteristics that we need that matches up with the Eurograte. We now have ticks across all the materials, so SolidWorks knows what everything is made from. Now we need to add the constraints. Now this is where we tell the simulation software how everything is held together. The default setting is bonded. Now that means that everything is glued together. That's perfectly fine for these treads because they actually are welded to the side stringer. However, the Eurogrid at the top just sits on top of the gantry plate, and it's also then the gantry plate is bolted to the side stringer. So we can't have them welded at molecular level because it's kind of as if they're joined perfectly. We need to put in those constraints. We also need to tell it how it's held. Now remember, we chopped this into 1/4, so the first thing I'm going to do is tell it this is symmetrical, so that actually all those loads are spread on all 4 sides, even though we're not actually meshing or modelling those other parts. It is the foot that stops this ladder from spreading apart, so we need to emulate the fact that there is a foot plate there, even though we deleted it out earlier. And I shall use a hinge constraint to do that. We have told it how it's held together and also where it sits in the world. We need to finish this off just finally by putting in that external load. So going back to the drawing standards, it's actually 2000 newtons applied per meter squared over the top gantry. In other words, 2000 newton meter squared of pressure on the top face as well. Let's go back to SolidWorks and build these connections. So we continue to work our way down our simulation tree, and here we can see the connections, and our global connection is set to bonded as I described earlier. So instead I'm actually going to put in some no penetration between the top of the Eurograte and our top actual gantry beam. So we just pick those 2 faces. Now I also need to do the same with the stringer and the top gantry bar as well. So I'm picking the 2 faces where they meet, and again I'm setting to no penetration. Now if that's how we left it, effectively when we put the simulation on, our top gantry would fall through the floor. We need to put these bolts in. So I'm going to use a bolt connector. So I pick the 2 circular faces on either side of where the bolt would be, and I can go in and I can tell the software to say, well, how big is this bolt? So we know that we want a 10mm bolt that's got an 18mm head, and I can even apply some torque. That's again after choosing the material for the bolt. So I'll put 25 newtons on there. If we give this a tick, then all I need to do is just pick the other 3 holes, so we then have all 4 bolts bolting this together. And then we can just give this a tick. So effectively we're emulating the strength of a bolt without the software having to actually mesh up or work out how strong a bolt's going to be. Now we need to add our restraints. So we need to tell SolidWorks how this is fixed in space. So the first thing I'm going to do is I'm going to add this symmetrical in. So we're doing a symmetry mate, just picking all the faces where it chops across the 1/4 that I chopped out. Not forgetting of course to do the other side as well. You can see from the preview there, this is how it's going to expand the solution out to take into account the fact that it's a complete set of stairs. But then what's stopping it from moving around? Well, that's where that foot plate was mounted. So I've got a couple of the components left over, but effectively the foot doesn't really move. So I'm going to stick it on here as what's called a rolling sliding. So that face can move around, but it can't go further down. Now I need to stop it moving from side to side, so I'm just using a fixed hinge around the actual shaft, and that'll stop it moving from left to right. And with that done, we've got all the restraints that we need to do for our simulation. That leads us with the external load. This is where we're going to apply that pressure. So I need to pick both the faces on the top of this little pad on the gantry, and we're going to put in 2000 newtons per meter squared, which is per the actual codes of practice. Before the software can solve this puzzle, it needs to actually break the calculations down into lots of little pieces. This is called meshing. Now thankfully there's not really much we need to do apart from just to mesh and run these results. So let's just show you that back into SolidWorks. Now we could actually skip the mesh stage completely and just click on mesh and run, and it will just do it, take the default settings. But what I'd like to do is just create the mesh just so you can see how it's solving this puzzle. So it's going to break it into lots of little triangular pieces, and then it will work out the calculations based on these little triangles. So here's our initial mesh, just lots of little pieces. And again, what we're going to do is we're just going to go and do a run now. So we're just going to say to the software, go and solve this equation. Now I've speeded up this, but the actual solution time took just over a minute, so it was 1 minute and 7 seconds. And then we're on to looking at our results. Just what are we looking for? Well, going back to the standards, obviously it cannot fail, so we need to check the mechanical strength of our gantry. The deflection needs to be 1/200th less of the span, which in this case works out at 7.5 mil. And also we have a maximum deflection between floors at 4 mil. Now in this case there is only the one floor, so that's just like an extra sanity check that we can do when we're interpreting our results. Okay, let's go and have a look. The first plot here is the stress in our design. Now if we have a zoom over here, we can see the maximum stress currently is 40 megapascals. So we need to see how that affects our design. So where are these high levels of stress? Well, as you would expect, we've got a little bit of stress happening around the bolts, but more importantly, we've got a lot of stress happening through where the actual foot is clamped onto our design. So there we see this is where our main stress is, but let's go and have a look at the material. So I know that the actual bracket for this is made of plain carbon steel. So if we look at the physical properties of this, we can see that if we change it to megapascals, we've actually got 220 before we hit our yield strength. And we're only getting 40, so we've got plenty of strength in there. However, the rest of the frame is made from 1060 alloy, and that only has a yield strength of 27.5 megapascals. So how can we check and get a good feeling for our design? Well, that's where we're going to use a factor of safety plot. The bracket at the bottom, that comes with the foot, and we don't make that, so I'm only interested in my factor of safety on my stringer and my top gantry bar. With them selected, I want to know how close they are to their yield strength. So what we can do here is we can have a look, and we've got our minimum factor of safety is nearly 1.6. So it isn't going to fail, it's actually 1.6 times stronger than it needs to be, but it's always nice to have a little bit of wiggle room here anyway. If we wanted a bit more wiggle room, then we could start to look to see, well, where could we help our design? So we've got quite a bit of stress that's happening around where the bolts, and also there's a fair bit of stress again just happening down at the bottom bracket piece. So we could just perhaps thicken up this stringer to get us a little bit stronger, but I'm happy with 1.5. We also need to know how much everything is deflecting, so we're going to do a displacement plot. So the actual displacement in the middle of our gantry is 1.29 millimeters. That's well inside the 4 mil and well inside the actual 7 mil that we actually require. So we're kind of over-engineered. The thing that I want to do next is I'm going to build up to a report. So it'd be nice to show all this as a complete ladder rather than just 1/4. So I'm just going to modify a couple of these plots now and just turn on the symmetry option. So it just shows a complete gantry and makes it look for a far prettier image. Finally, I want to show everyone my results. So I'm going to generate out a report. Now there's a lot of information that we can have, but I prefer to kind of keep it down just to the bare minimum. So basically, I want the material properties and some plots. Let's put my name in, and of course this was all done for T&I Solutions. I'm going to publish this to a Word document, doing it into A4. So it's going to go away now and it's going to create all the snapshots of all the images, and it's going to compile this into a very good report. So if we scroll our way down, we can see the material information, we can show how we restrained it, we can look at our stress plots, our displacement plots, our factor of safety plots, and then what we need to do is we need to write our conclusion. So this is basing it back on the information that we took from our standards. So now the minimum factor of safety, It wants to be at least 1, so we actually designed that to 1.5, so we're actually well inside the actual standard there. We also were concerned with the displacement. Well, we got that information again, so we just need to put that into our conclusion that we know it was 1.3 mil deflection, which is well inside the actual maximum allowed, which in this instance was 8 mil or 4 mil if it was adjoining plates. Remember, there was 2 tests that we needed to apply. One where we've actually got 2000 newtons applied across the whole of the gantry face, and another one where we had 1500 newtons just applied very locally. So what I'm going to do here is I'm just going to copy my original study. Let's give this a name, so this is going to be our localized study. And that's going to copy all of the actual original study. So that's all the materials that are put in, all the constraints and the loads. So I can go into here now and I can take my original load that we put in there. I'm just going to suppress that, and I'm going to add a force just acting on this little quarter that we created. Now we only need 1/4 of the load, so that's 375 newtons, and then we can just basically rerun the study. Again, I've speeded this up a little bit. Now if we go through all our results, we can see again that our stress really hasn't changed within our design. Our displacement has increased to 3 mil, which again is well within standards. And if you look at our factor of safety plot, that's been reduced slightly down from 1.5 to 1.3. So all in all, we're still good even on this second study. So does our design come up to standard? Well, the first thing was it should not fail. Well, we exceeded that one thankfully with a minimum factor of safety of 1.3. I suppose the next thing was the deflection. Well, we needed to be inside 7.5 mil, and we were, because we only had 3 mil deflection. And that also meant that we exceeded the actual standard as well for a minimum displacement between plates. Now normally with these presentations I upload the model onto GrabCAD to let people to download it. Unfortunately these aren't my models, so I can't do it this time, so please don't ask me to send you a copy of the model because this is company data. Hopefully you've enjoyed this presentation. If you have any questions, then you can either ask them to me directly via my email, or you can leave them in the comments section. I'd also like to take this time to thank Robert Smith, who's part of our simulation team, who basically just cross-checked all my work to make sure that I wasn't doing anything stupid. So thank you for your time. Goodbye.